The topic of today's video will be Cauchy's theorem, and we are extending that topic or complex integration, right? So this is a part of complex integration, but this time the contour, means the curve, will be closed, right? So starting with the definition of domain, I will recall the definition of the domain, which is that a simply connected open set is called domain, or you can say that an open set in which any 2 points can be connected by a sequence of polygonal lines, that is called a domain, right? So I am recalling the definition of domain, right? And an example of domain is this. This is an open set without boundary, right? So you take any 2 points on it. This point is one point, this is another point, and you can join these points by sequence of polygonal lines this way, right? And these lines lie inside the domain, lie inside the set, right? So this is an example of a domain. Right. Okay, now I will define simply connected domain, right? Domain, simply connected domain A, right? Another is multiply connected domain, right? You can see that this is a domain in which any 2 points can be connected by a sequence of polygonal lines. The first thing is that, and all of those lines should lie inside the set, right? Then we'll call it domain. I should give an example of a non-domain, and which is like this. Right. So you can see that this is an example of a non-domain. If you take any 2 points, 1 point here and 1 point here, then you cannot join these points with a sequence of lines and all of those lines lying within the set, right? But individually they are domains, right? If you see this is a individually it will be a domain. It is also a domain, but collectively they will not form a domain, right? Because taking 1 point here, this part, and another point this part, right? You cannot join these 2 points by using these sequence of lines, and all of those lines should lie inside the set, right? This is an example of not a domain, right? Okay, now I will define simply connected domain, right? So simply connected domain, I will draw the figure, and simply connected domain is this. Right. So this is an example of a simply connected domain, and why we are calling it simply connected. I will draw a small closed curve inside it, and this closed curve is this curve. You can see this curve, right? C, right? And this is domain, simply connected domain, simply connected domain, right? And why we are calling it simply connected? Because if we take any curve, closed curve inside this domain, right, and we shrink it, right, then that curve can be shrunk to a point without leaving the domain D. You can see that this is a domain D, and if you shrink this curve, this is a closed curve, right, and if you shrink this curve, this will shrink to a point, right, and obviously this curve will not leave the domain D, right? Means while in the process of shrinking, the curve will not leave this domain D. That's why we are calling it a simply connected domain, and that is true for all of such simply closed curve inside this. If I draw another curve here, like this. You can draw another curve here, this one, right? And if you shrink it again to a single point, right, then it will not leave this set, right? So this is an example of simply connected domain, and a domain which is not simply connected will be called multiply connected. I will draw a diagram here of multiply connected domain. Multiply connected domain, right? And you will see that this domain, obviously this is a domain, right? Why it is domain? Because you can take any 2 points on it, take this point and this point, then you can join these points by a sequence of polygonal lines, right? And all of those lines lie within this set, right? So this is a domain. First thing is that. Second thing is that why we are calling it multiply connected, because if you take, similar to this, if I take two curves like this one, if I take a curve here, closed curve, right, C1, okay, then it can be shrunk to a single point without leaving this domain D. That's fine. If I take a curve here like this, again this can be shrunk to a point without leaving this set, right? But if I take a curve here and closing this hole like this, right, you can see that this is my C3, right? And if you try to shrink it, then obviously it will leave this set, it will leave this set, right? In order to shrink this curve to a single point, it will go like this. It means it will appear like, due to the surface tension, it will go to shrink and will shrink to a point, but that point will leave the domain D, right? So intuitively you can say that a domain is simply connected if it does not have any holes inside it, right? You can see that it is not having any hole, right? Okay. And if it is having hole like this one, you can see that this is a hole, right? So in that case it will not be a simply connected domain, we'll call it multiply connected domain. In this case it is a doubly connected domain, because you can see that one hole for doubly connected. If it has two holes, then it will be triply connected, right? So doubly connected. Right, this is a domain D. Okay. So in our statement of Cauchy's theorem, we will assume that the nature of domain D will be simply connected, right, initially. Okay. So moving to the theorem of statement's theorem, Cauchy's theorem, that is Cauchy's theorem. The statement of the theorem is if f is analytic in a simply connected domain D, right, and f dash is continuous in D, right, then for any closed curve C inside D, we have equal to 0, right? Means first thing is that you need a domain D, right, and that should be a simply connected domain D like this one, right? Okay. And there is a curve C, closed curve C, lying within that domain D like this picture, right? This is a domain D, right, and this is simply connected domain D, and what do you need? You need C, closed curve C like this one, right, and f is analytic on this whole domain D, right? Then for any closed curve C inside this domain D, the integral along that curve will be equal to 0, right? Okay, and we will prove this result, right? It assumes that f is analytic in a simply connected domain D, means if f is analytic, then it will satisfy Cauchy-Riemann equations, right? And another thing is that f dash is continuous, and if f dash is continuous, then it's u and v part, because f is equal to u plus eta v, then u and v will also be continuous, or you can say that partial derivatives are also continuous in domain D, right? And then we'll take a closed curve C inside D, and then we'll prove this result, right? Okay, but to prove this result, we need two things. First is the Cauchy-Riemann equation, and the second is the Green's theorem, right, from the real calculus, right? And okay, I will start with Cauchy-Riemann equation first. Since f equal to u plus eta v is analytic, right? Therefore, by Cauchy-Riemann equations, del u over del x equal to del v over del y, and del u over del y is equal to negative of del v over del x, and these are by Cauchy-Riemann equations, right? Okay. Now, evaluating this integral C f z dz, this will be actually equal to the value of f z is u plus eta v, and dz is actually dx plus eta dy, right? And you know that this symbol represents that the contour C is closed, right? That's why we are putting a circle here, right? Okay, then on writing it as u dx, and that will be minus v dy plus eta times, eta will be here, v dx and plus u dy, right? And okay, fine. Then at this point you can see that the integral along this closed curve C is actually the sum of two integrals, right, along curve C. And if you try to use the Green's theorem at this point, I will first recall the Green's theorem. What is that? Green's theorem at this point. Recall Green's theorem, right? And the theorem is that if p as a function of xy and q as a function of xy are continuous with their partial derivatives inside region capital R bounded by a closed curve, let me call that curve T, right? Then integration of p x y dx plus q x y dy equal to line integration actually along T is equal to double integration along the region R del q over del y minus del p over del x dx dy, right? So this is a statement of Green's theorem. I have written it incomplete. The theorem is if p and q are functions of x and y and they both are continuous with their partial derivatives inside region R, right? And that region R is bounded by actually a closed curve T, right? You can think of a closed disk, right? If you take a closed disk, then the surface of the disk means the surface of the disk is this region R, and the boundary is the curve capital T, right? And then the line integration of p dx plus q dy is equal to the double integration over that region del q over del y minus del p over del x dx dy, right? And this is the diagram for it, and this theorem holds on xy plane, right? Since we are using dx dy here, the theorem will be true for xy plane. On xy plane, we have something like this: a region R bounded by curve T, right? This is the region R, and it is bounded by a closed curve T, right? You can see that this is a closed curve T bounding something inside it, right? And that is called region R, right? And you can see the direction of this curve, that is counterclockwise, anti-clockwise, right? Then this line integral of some function p dx plus q dy along this curve T is actually equal to the surface integral, or you can say that double integral over the region R, right? Del q by del y minus del p by del x dx dy. Means the Green's theorem relates the line integral to the surface integral, right? And most important thing is that that surface is bounded by that curve, right? Means you are going to integrate something over the boundary of some surface, right? Then the theorem switches the line integral in terms of surface integral, right? Okay, so this will be like a prerequisite for this Cauchy's theorem. I will be using this result here, right? And you can see that in place of T, right? T is a closed curve. We have capital C here, right? Capital C. So C is a closed curve this time, right? And in place of capital R, region R, we have domain D, right? Okay. Then I will going to use this theorem for this integral and for this integral, right? Okay. Now equation number 1 from equation 1, right? Integral C fz dz equal to this thing, using Green's theorem on this integral, that will become del q over del x. Okay, fine. Del v over del of negative v, actually that is minus v, right? Over del x minus del u over del y dx dy, and this will be replaced by d, right? And line integral, right? Integration along a curve is converted into integration over domain D, right? Means this single integral is converted into double integral using that Green's theorem, right? And for this one, plus eta times this will become del u over del x minus del v over del y dx dy, right? And here I will have double integration domain D, right? So this step is just the reflection of this Green's theorem. By using this Green's theorem, each of these two integrals can be written in this form in the terms of double integration, right? And now I will use Cauchy-Riemann equation. And one more thing is that I can only use Green's theorem here whenever it is given that u and v are continuous and their derivative is continuous. Means f dash is continuous is assumed here, right? Due to this condition, I was able to use this Green's theorem, because see here, Green's theorem statement, it says that the partial derivatives inside the region are continuous. Continuity of partial derivatives is required, right? And that is essentially the hypothesis of the Cauchy's theorem, that f dash should be continuous in G, right? That's why I am able to use this Green's theorem here in my equation number 1, right? Okay. Then it will become negative sign will appear here, okay, and I will use Cauchy-Riemann equations using CR equations. Here I will get integral C fz dz. I think that will become minus of del v by del x is equal to minus of del u by del y, and actually del u by del y is equal to negative of this thing, so ultimately it will be 0, right? d0 dx dy, and again del u by del x is equal to del v by del y by Cauchy-Riemann equations, so it will be 0 dx dy. So ultimately the result will be 0. So this is the proof of Cauchy's theorem, right? So I will again repeat the statement of Cauchy's theorem with a diagram here. See that f is analytic in a simply connected domain D. I will draw a random domain D simply connected. Let me draw it with different color, right? So this is and simply connected domain D. You can see that there are no holes inside it, right? And the boundary is it is boundaryless. That's why we are calling it open set, right? Simply connected domain D, right? And inside this domain D, we have this any closed curve C. Let me draw a closed curve C like this one. This is a closed curve C. It can be of arbitrary shape, right? So this is my closed curve C, right? And the theorem says that f is analytic inside this red colored region, means simply connected domain. F is analytic everywhere on this red colored region, right? Red colored domain, right? And this is a closed curve inside D, right? C should lie within the D, right? Okay. Then the line integration of fz along the C, if you integrate your f function f over the boundary of this C, right, then the answer will be 0, right? So this is the picture you should be keeping in your mind when you apply this Cauchy's theorem, right? And obviously this domain, right, lies on jet plane, right? I will write jet plane here, right? You have jet plane, complex plane, right? And on complex plane you have a simply connected domain D, right? Okay. And inside that simply connected domain D you have something, a closed curve C, right? And you want to integrate your f along this curve C, and you know that f is analytic over this red region, right? Then the integration along any such curve, closed curve, which lies completely inside D, will always be 0, right? No matter what is the shape of that curve C, whether it is a triangle, rectangle, ellipse, any shape, but it should be closed, right? So this is Cauchy's theorem. And after several years, a French mathematician, Goursat, redefined this theorem or did some manipulation on this theorem. He told that this condition is not required. F dash is continuous on D is not required actually. Then this theorem is still hold, right? I will rewrite that statement, Cauchy-Goursat theorem, because the French mathematician named Goursat redefined this theorem, and he actually removed this condition of continuity of f dash inside D. Means this condition f dash is continuous in D is actually not needed, right? Even then this theorem hold, right? I will rewrite that statement, Cauchy-Goursat theorem. Cauchy-Goursat theorem, and it says that if f is analytic in a simply connected domain D, right, then for any closed curve inside D, its line integration is 0, right? You can see that this condition has been removed in the theorem, in the statement of Cauchy-Goursat theorem, right? And its proof is quite complicated and very long. It needs 2 or 3 lemmas to prove this result, right? Because this theorem is simple, means as compared to this, it needs less hypothesis, but the proof is complicated, right? But we'll go with this Cauchy's theorem because the result is still the same. So we'll carry on this statement, right? Okay, I will take examples of this Cauchy's theorem. Example number 1. Evaluate the integration over closed curve C, because this symbol is used, it indicates that this curve C should be closed curve, right? E to the power z dz, where C is any arbitrary curve inside complex plane. C. I will write it as like this C. This is for complex number C, and this is closed curve C, right? So, however, the shape of the curve C is not known, but it is only known that the curve is closed due to this symbol, right? Solution. And let me draw the y and x-axis, right? And this closed curve C, I will draw it with black marker. Arbitrary curve can be drawn anywhere, right? Closed curve C, fine. And where is my domain D? Because the theorem needs domain D. Where is the domain D? Domain D is actually the whole complex plane, right? Means everything you see here is the domain D, right? And the function, you can see the function, this function e to the power z. You focus on this function, right? E to the power z. As I should draw the domain D here also with my red marker. So this is the domain D, the whole complex plane, right? Here also negative side, this side, the whole complex plane is a domain D, right? It is extending infinitely in all directions, right? This is a domain D. Okay, so as you can see that this function e to the power z fz equal to e to the power z is analytic inside C, right? Obviously, f is e to the power z is an analytic function. You can check it by using CR equations, right? It will satisfy CR equations everywhere, and it has continuous partial derivatives everywhere, right? So this is an analytic function, or you say it entire function, because it is analytic over the whole complex plane. So this function is an entire function, right? So it is analytic everywhere over the red region, right? Means all of the complex plane, and obviously it will be analytic inside C or within C, right? Then, or should I write it within C? Within C. Then, by Cauchy's theorem, integration C e to the power z dz equal to 0, right? So I have used that theorem. No need to integrate it, because you know that the result will be 0, right? By Cauchy's theorem, fine. And obviously this result means the integration will always be 0 as long as this function is an entire function. Means if we take sin z here, sin z dz 0, cos z dz 0, right? Any polynomial multiplied by then dz equal to 0. Constant function dz 0, right? Because all entire functions when integrated along a closed curve give the answer 0, right? The example number 2, and this time I will take evaluate integration along closed curve C and 1 over z square dz, right? Where C is an ellipse, right? And the ellipse has equation x minus 1 whole square by 1 by, or should I write it 4, plus y minus 1 whole square, or should I write it 2, equal to 1. Fine. So this is an ellipse centered at 1 comma 2, right, and with axes 2 and 1, right, major axis and minor axis. Solution. First we'll draw this ellipse, x-axis and y-axis, right, and I will draw this ellipse, and that ellipse will be x minus 1 whole square upon 1 by 2 square. You can take this 4 here in the denominator, 1 by 4, right, and then you can write it as 1 by 2 square, and it will be y minus 2 whole square over 1 square, and then the center of the ellipse will be 1 and 2, means 1 here and 2 here. Okay, fine. And x, along x it will be 2, it will be here, okay, 2, and it will be 1, it will be like this. This point is 1. Fine. You can see that the center is 1 comma 2. This point is 1 comma 2. This is 1. This is 2. So the center of the ellipse is 1 comma 2, and x minus 1 whole square over 2 1 by 2 square. Sorry, I think it should be small, because it's 1 by 2 square. It will be like this. Fine. One by 2 square plus y minus 2 whole square over 1 square equal to 1, right? Okay. So 1 comma 2 is the center of the ellipse, right? And you can see that the length of the major axis, semi-major axis, is half, right? And minor axis it is 1, right? Okay. And the important thing is that this function fz, you know, this function fz, is it analytic within this contour C, right? This is your contour C, okay. And you can see that this function here, fz equal to 1 over z square, is analytic within C, right? However, we know that z is equal to 0 is the singularity of this thing, right? Z is equal to 0 is the singular point of this function, and fortunately that z is equal to 0 is not lying within this C, it is outside. Z equal to 0 is here, right? So our ellipse, means our contour C, is not enclosing any singularity of this function. So we can say that this fz is analytic within this contour C, right? And then we can freely use that theorem, because one of the hypotheses of this theorem is that f should be analytic in a simply connected domain D, right? F is not, however, f is not analytic at z equal to 0, but luckily z equal to 0 is outside this C, right? Okay, is analytic within C. So by Cauchy's theorem, or Cauchy-Goursat theorem, you can write it as integration C 1 over z square dz will be equal to 0, right? Okay, so we have taken two examples. The first example is that when the function has no singularity anywhere, right, and the answer is 0 by using this Cauchy's theorem, right? In the second example, we have taken 1 by z square, which has a singularity, one singularity at z equal to 0, but luckily that singularity was outside our closed curve C, and again we use this theorem, right, Cauchy's theorem, and the result is again 0, right? And if you want to draw the domain D here, means the red region, then I will draw it like this. my region will be like this. And since you know that function is analytic, not analytic at z equal to 0, means the boundary of the region should not include this z equal to 0, right? You cannot draw this region like this. In that case, z equal to 0 will be enclosed in your domain D. So your domain D must not include this z equal to 0. This is a danger point, right? So you can extend this region here, you can extend this red region here, but not here, right? So this is the domain D. Fine. So we were able to use this Cauchy's theorem due to this singularity lying outside the domain D, or you can say that the nature of the curve was such that it was not enclosing any singularity of this function f z, right? But what happens if this curve encloses the singularity, right? Had we given an ellipse of the form x square plus y square equal to 1, means an ellipse centered at origin, right, and having both axes equal to 1, then what will happen in that case? Your ellipse would be here, right, and that would enclose the singularity. Then can we use this theorem, Cauchy's theorem? No, right? This theorem should be modified for those cases when the curve C encloses this singularity, right? So I will rub this first. Cauchy's theorem for multiply connected domain, right? Cauchy's theorem for multiply connected domain, right? So in order to use this theorem for cases when the singularity of the function lies within C, right? Okay, then we'll start with first a multiply connected domain. I will draw one or two holes inside it, right, and we'll derive the result, and then we'll generalize the result for n holes, right? Okay. So this is a multiply connected domain. You can see that this domain, right, and it has holes inside it because we are saying that it is multiply connected. This is the first hole, right, second hole, right. Right. So this is an example of multiply connected domain. Multiply connected domain, or more precisely it is triply connected domain because it has two holes inside it, right? Okay, and you can see that if some function is given, I will write it here. Let f is analytic inside a multiply connected domain like this, right? And C1, C2, dash 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 Ck are closed simple curves inside C, right? Then line integration of fz dz along the closed curve C is actually equal to the summation of integrals f z dz, and k starts from 1 to n, right? Now should I write it as n? Okay. And let me draw this C1, C2, C1. C1 is the curve enclosing the first hole, right? Okay. And C2 is the curve enclosing second hole. This is a C1, this is a C2, and similarly you can draw C3, C4 up to Cn. I have drawn only two holes, and C is the curve here like this. This is a C, and the red region is the domain D, right? Domain D, multiply connected domain D. So you can see in picture that first thing is that you need a domain D that should be multiply connected, having one or more holes inside it. I have made only two holes, fine. And C is the curve. You can see this curve, closed simple curve, right? The bigger curve enclosing the two small curves C1 and C2, and C1 is a curve enclosing that hole. C2 is another curve, simple closed curve enclosing second hole, and so on. And C is the curve enclosing all of those C1, C2, and Cn, right? Okay. Then the theorem says that, right, means modified version of this Cauchy's theorem for multiply connected domain. This time we are focused on multiply connected domain, right? In that case, the line integration of f along this outer curve C is actually equal to the sum of integrals over these small curves C1, C2, and so on, right? You can see the summation is present here, right? And why this is true means why this is a direct consequence of this Cauchy's theorem when applied on such a multiply connected domain. We'll see a small proof for it, right? Proof, right? Make cross cuts in multiply connected domain D such that it becomes simply connected, right? As shown in figure, as shown in the figure, new figure. I'm going to draw the new figure. What do you want? I want to use that Cauchy's theorem, and we know that this Cauchy's theorem was for simply connected domain, but this time we are facing a multiply connected domain. Then what do we want? I want to convert this multiply connected domain into a simply connected domain, right? And that can be done by making cross cuts, right? Cross cut means, I will show here in diagram how to make a cross cut in order to convert a multiply connected domain into a simply connected domain, and then we'll be able to use that Cauchy's theorem, right? We want to use that Cauchy's theorem. Okay. So this domain, you see this domain, I will copy this domain again, right? Okay. You can see that the first hole, right? And the second hole, right? Okay. And we had this curve, outer curve C, right? C, right? And we had two curves C1 and C2 in the original picture. So this is my C1, C1, and this is C2, right? And the outer was domain D, right? And in order to show that this is a domain, I will put red dots everywhere, right? Okay. Now the two pictures are almost identical, right? And you can see that since we are going to make cross cuts here, right, and those cross cuts are made by joining these outer curves C with these inner curves C1 and C2, like this one. See, if I make a cross cut here, here, like this, right, both directions, right? This point is A point and this is B point, right? And here a cross cut here, and you can see that if you move anti-clockwise like this way, right, then you can enter along this cross cut from this point in this way, and then you will go like this, right? This point is B point, okay, and then on moving along the boundary of C1, then you will go back along this arrow, because this arrow has both directions, in the inside direction and outward direction. Then you will go along this, like this one, and then here, then you will enter from here by this cross cut. This point is C point, this is D point. Then you enter along this line, then you move along the boundary of the C2, then you will come back along this DC path, and finally here, right? So you can see that by introducing these two cross cuts CD and AB, right, this multiply connected regions becomes simply connected. Why? Because this time, originally, you can see this C1 curve, right? You can shrink this C1 to a single point, but that will leave the domain D, because this is a white gap here, right? But in this picture, you cannot put a curve like this, closed curve like this, means you cannot put a closed curve enclosing this hole or this hole, because you have made a cut here, right? You cannot put a closed curve like this. You have to put that closed curve either on the left of this cut or on the right of that cut, and in that case, shrinking that closed curve, right, will not leave the domain D, means that this picture is now become simply connected, right? Okay, okay, and you can see that there are two cross cuts AB and CD, fine. And since it is a simply connected domain, then I can use the Cauchy's theorem here, because Cauchy theorem can only be applied on the simply connected domain till now, right? Okay, so using Cauchy's theorem on the simply connected domain here, integration C fz dz plus integration along AB, means this path, AB path, fz dz, then we'll come back from this path, that will be BA fz dz, then along closed path C1 fz dz, then plus CD fz dz plus DC fz dz C2 fz dz, that should be equal to 0 by Cauchy's theorem, because this time this whole curve is simply connected, right? And you can see that along this C, this integral represents the integration along this C, and along AB, this one, then BA, this integral, then C1, this integral. And one more thing, you can see that along C1 the direction is anti-clockwise, right? So making an anti-clockwise direction like this small arrow, right? And if you move along C1, you can see that the direction is clockwise. I will make a clockwise arrow here like this, right? And similarly along this C2 curve, the direction is again clockwise, right? So see these arrows, right? This is an up arrow counterclockwise, and these are C1, along C1 and C2 the arrows are clockwise, right? So as you know that this AB, see this AB, this is a small part of line, right? So line or curve, you can say at curve, right? Integration along AB is equal to the negative of integration along BA, means the limits will be changed, lower limit A, upper limit B, and in the reverse case the lower limit will be B and upper limit will be A. So these two integrals will cancel each other, right? And similarly these two integrals CD and DC will cancel each other, right? And we'll be left with these three integrals, first, second and third, right? Okay, integration C fz dz, and you remember this, the direction of the arrow, it is actually anti-clockwise, right? You can see from picture, and this one and this direction is clockwise, verify from figure, C1 fz dz, and then plus this direction again C2, it is again clockwise, fz dz equal to 0, because these terms cancel each other, right? Fine. And then you can bring these two integrals on the left and right hand side, fz dz equal to, taking these two integrals on the right hand side, and that will produce a negative sign before these two integrals, but absorbing that negative sign by reversing the direction of these arrows, we can also do that, means these actually are clockwise circles, right? And I will replace them by anti-clockwise circles in order to absorb my negative sign on the right hand side. So I will, this time I will draw anti-clockwise circle fz dz along C1 and along C2 fz dz, right? So this is a small proof when we considered only two holes, right? And you can see that the arrows have same directions, right? Anti-clockwise, anti-clockwise, anti-clockwise. So we can generalize this result for n holes, and that result will be this one, right? In general, for n holes inside multiply connected domain, the result will be integration C fz dz equal to the sum of all such integrals, and writing that, denoting that sum by summation k equal to 1 to n integration fz dz c k, right? And generally we don't put an arrow here, right? Whether you put an anti-clockwise arrow or clockwise direction, both sides are same, right? Okay, right, fine. So now I will take example of such a multiply connected domain, right? Okay. Before taking its example, I will add one more thing, that this theorem, what does it do? It actually replaces the contour that was present inside the domain D by some simpler contours C1, C2, C3 and so on. Means the integration on the outer contour is actually equal to the integration on the inner small contours, right? So this will be the main highlight of this theorem for multiply connected region, and I will be going to use this result in deriving a small but useful fact, right? A useful result, right? And this result will be used in the later part of our numericals, right? And the result is integration, closed integration along closed curve C dz over z minus a to the power, let me write it, n equal to 2 pi eta if n is equal to 1 and 0 if n is not equal to 1, and this where n is an integer, right? And a is a complex number inside lying inside contour C. C is closed curve, right? So this is the useful result which says that integral of dz over z minus a to the power n is equal to 2 pi iota if n is equal to 1, and for not equal to 1 the result is always 0, right? And we will be using this result to prove this, right? Okay. Solution, or we should say proof. If n equal to 1, right, then capital I equal to integral c dz over z minus a, right? And c is a contour, right, arbitrary of arbitrary shape containing this number a, right? You can see that your function is 1 upon z minus a. Here fz equal to 1 upon z minus a is not analytic at z equal to a, right? Hence making a small circle C1 around A, that is mod z minus a equal to small r, right? Or you can take it mod z minus a equal to 1, shown in figure like this. You have this y-axis and x-axis, right? And this z is equal to a is somewhere. Let this point be z equal to a, right? And this is your contour C. This is your contour C. It's a complicated contour, or direction, or I should say the orientation is anti-clockwise, and its shape is arbitrary. You can see that the shape of this contour C is arbitrary shape, right? So this contour C is enclosing the singularity A, right? And you again see that this function is analytic, not analytic at z equal to a, and every except z equal to a it is analytic, right? So I can draw my region like this with red dots. This is my region because this function is analytic everywhere but not at this point, right? So you have to leave this point, a point, right? Make a hole here. Automatically a hole will be created at this point because the function is not analytic at z equal to a, and within this region it is analytic, right? So this is the domain D, and it is extending towards infinity, right? The red region. Okay. Now what I will do, since it is a multiply connected region, because you can see that there is a hole at z equal to a, right? So I have to remove this hole, or again I should say that I have to make this f continuous on my domain D, and for that I have to put a curve here, put a small circle here like this one, right? And this circle is actually C1, right? C1, and this circle is centered at z equal to a. You can see that, right? And having radius r, small r is the radius, right? Or you can take r equal to 1, 1 by 2, anything, right? So in this way, this region looks multiply connected, right? And now I will be going to use this result, right? The original integral along the curve C, given curve C, is actually equal to the sum of integrals along the smaller curve C1, C2, and so on, right? In this case, I have only smaller curve C1. C is the bigger curve, right? The curve on the left hand side, integral, and here we have C1, the smaller curve, right? So actually the integration along this outer curve will be automatically equal to the integration along this small circle of radius r and centered at small a, right? Or you can take r equal to 1, 1 by 2, it is your choice, because no matter what is r, but the important thing is that this curve C1 should lie inside this C, because that is the hypothesis of this theorem, right? Okay. So using parametrization and the choice of this circle, why we choose a circle, why don't we choose a square or rectangle, right, around that z equal to a? The reason is that because z equal to a, mod z minus a equal to r is the equation of circle, obviously, and it is the easiest equation which we can parameterize and then apply integration, because the parameterization for a circle is very easy. Z minus a equal to r times e to the power eta theta, and theta varies from 0 to 2 pi. You can see from here it's a complete circle, right? Okay, now I will evaluate this integral using parametrization, right? So using this theorem, right, means the actual integral, then the actual integral which was asked around the curve C, right, now it will be equal to the smaller curve, means the complicated curve C, right, is replaced by a simpler curve C1, and that is actually a circle. So this is the point where we use this theorem, right, dz over z minus a, right? Fine. Now after using this theorem, I will integrate this by using the new normal techniques of integration which we discussed in our last video, and that is the parametrization, right, where I should mention here where C1 is mod z minus a equal to small r, right? And to parameterize this circle, now z minus a equal to r times e to the power iota theta, and where theta changes from 0 to 2 pi because it is a complete circle. Now on differentiating it, I will get dz equal to r iota e to the power iota theta d theta, right? And plugging these values here, I will be getting, therefore I equal to 0 to 2 pi, and on plugging these values I will be getting iota d theta, and on integration it will give me 2 pi iota, right? So this is the proof for this one. For n equal to 1, we have this answer 2 pi iota, right? You can see, and I will call it part number A, right? Fine. So the important thing about this is that no matter what is the shape of this curve C, right, you will always replace that curve by a smaller circle, right? Circle is the easiest equation to parameterize, right? And the answer is can be directly written as 2 pi times iota, provided this A lies within C, right? Okay, now I will take the another case when n is not equal to 1, and we'll break that case into two sub cases further, for positive n and negative n, right? I will call it case number B, right? If n is less than 1, and since n is an integer, so n can be 0, minus 1, minus 2, minus 3, and so on, right? In that case, then your function, this function, you can see this function fz is 1 over z minus a to the power n, and if this is 0, then it will become a constant function, right? If it is n equal to minus 1, then it will become fz equal to z minus a. If it is n equal to minus 2, then it will become z minus a whole square. You can say that every time for n less than 1, fz will be a polynomial, right? Because for negative values of n, that is a polynomial of the form z minus a to the power n, positive power, right? And for n equal to 0, this is a constant, and constant is a polynomial also, right? Then fz is a polynomial of the form z minus a to the power n, right? And you know that a polynomial is an entire function, right? Analytic function everywhere. And using Cauchy's theorem, right, means when fz is an analytic function inside contour C, then the result is always 0, right? Using Cauchy's theorem, integral of fz dz phi, and here we have C equal to 0, because fz being a polynomial is an analytic function inside closed contour C, and the result is 0 by Cauchy's theorem, right? Okay. Now the third case, if n is just 1 and greater than 1, right, means n can be 2, 3, 4, and so on, then I will be equal to integral C dz over z minus a to the power square if I take n equal to 2 or n equal to 3, right? Means 2, 3, 4, 5, 6, anything, right? Or you can use this point also, this point. Okay, fine, I will do it again. Let me take n equal to 2, right? Let n equal to 2. Then I will be getting this. Using parametrization, it will give me I equal to, I'm not writing that again, this parametrization. You can use it again and again, right? then it will give me I equal to integral 0 to 2 pi, and I think I will be having eta times e to the power eta theta, and that will be cancelled, e to the power eta theta, and in the denominator I will be having e to the power eta 2 theta d theta, right? And you can see that eta will come outside, 0 to 2 pi e to the power minus eta theta d theta, right? And since again this is a periodic function of period 0 to 2 pi, as we discussed in our last video, the answer will be 0, because it's a periodic function with period of 2 pi, the answer will be 0. No need to evaluate this, right? Right. So for any case when n is not equal to 1, case B and C, you can see that the result is 0, right? So we will use this result, a useful result, in our numericals, right? I will make a box on it. We'll be using this result directly, right? And I am again repeating the result that for n equal to 1, right, the answer is 2 pi eta, and for any other number, integer, other than 1, the answer is 0, provided this A should lie within C, right? Okay. Now we'll take examples of this. Example number 1. Evaluate I equal to integral along closed curve C z over z minus 1 whole square dz, where C is mod of z minus 1 equal to 1. Fine. Solution. The first thing is to draw this curve C, right? The circle is centered at 1 and the radius is equal to 1, right? So this is a curve C. Z equal to 1. Now obviously this point will be Z equal to 2, right? Fine. X axis and this is Y axis, right? And you will see that, see this function f z equal to z over z minus 1 whole square. You can see that this function is not analytic at z equal to 1, because denominator is becoming 0 at z equal to 1, means that z equal to 1, the function is not analytic, right? And that is this point, z equal to 1, means the function is not analytic at this point, right? It indicates that we have to draw a small circle here, right? Because that will give rise to a multiply connected region. You cannot say that the function is analytic inside this curve C, right? So you have to do something to avoid this singularity. You have to make a small circle here, fine. Or yeah, first me factorize it in terms of partial fractions. If I want to use this result, right? You can see that you want to use this result, right? But the problem is that this thing, z thing, right? We should have 1 in the numerator in order to use it, right? Okay. Here fz equal to z over z minus 1 whole square, and using partial fraction, we can write it as 1 over z minus 1 whole square. I should have 1, yeah, 1 and 1, right? Using partial fractions, right? Assuming this equal to a upon z minus 1 plus b upon z minus 1 whole square, and then on taking LCM and comparing, you will get a equal to 1 and b equal to 1, right? Okay. Or you can write it directly by using hit and trial method, as I have written it, using partial fractions. Fine. Okay. Now capital I equal to integral, so fz will be replaced by this thing, c dz over z minus 1 plus integral c dz over z minus 1 whole square, right? And now you can see that this is a curve C, right? And it is enclosing only one singularity, right? It means that C and C1 are same, right? Actually, the idea of choosing C1, C2, C3 and so C4 and so on in multiply connected region is that every CK, means every C1, C2 or C3, C4 must enclose one and only one singularity, right? Fine. And you can see that this curve is enclosing just one singularity, so it can be treated as C1, right? Had there been two singularities here, means z equal to 1 and z equal to half and z equal to 1, then I have to draw two curves C1 and C2, enclosing z equal to 1 by 2 and enclosing z equal to 1. Means every CK must enclose only one and only one singularity, right? So this is fine because this is enclosing one singularity, so this will work as C1, right? Okay. So I will not draw again C1, C2 and so on. This is fine. Okay. Now I will use that formula. You can match this. Here we have n equal to 1. The power is 1. So the answer will be 2 pi eta. 2 pi eta, right? But before writing 2 pi eta, you first ensure that this a is equal to 1 is lying inside this. This 1 is lying inside this curve C. This point is lying inside this curve C. You can see that 1 is lying inside C, right? Then you can use that formula. Okay. Again, see here, this A is again lying inside C. See from picture, right? Okay. So this is 2 pi eta and this will be 0 because this is not n equal to 1. So the answer is 2 pi eta, and we have used that result. I will call this result A. Let me call it result number A, right? Using A. So this is the answer 2 pi eta, right? Taking another example. Example number 2, right? Evaluate I equal to integral along closed curve C. I take dz over z square minus 1, where C is mod z minus 1 equal to half of 1. Fine, that's fine. Okay, 1 minus 1. Okay. So this is my circle, right? Solution. First I will draw the curve C, right? This is the y-axis, this is x-axis, and here you can see that the circle is centered at z equal to 1 and the radius is also equal to 1. The circle will be similar to that one. Fine. This is your circle C, right? Okay. Now you can see that the singularity of this function, to find the singularity, you can put the denominator equal to 0 and that will give you z equal to plus minus 1. It is very simple. So z equal to 1 is the singularity. One singularity is here, z equal to 1, right? And minus 1 is the another singularity, z equal to minus 1, right? And you can see that this time we are having two singularities, while in our last question we had only one singularity, right? So in this case, I have to draw two circles, right? The first circle should be C1 enclosing this singularity, and the second circle should be C2 enclosing the other singularity z equal to minus 1. But no, we cannot draw C2 because if you again remember the hypothesis of the theorem is that all C1, C2, C3, C4 and so on must lie inside C, right? So there is no point to make a circle here because this point lies outside our curve C, right? So the only point of interest will be this one, z equal to 1, right? Okay, so for that I have to write it in terms of partial fractions, right? Okay. Here fz equal to 1 over z square minus 1, and that is actually equal to z minus 1 plus 1 over z plus 1, and on taking LCM that will produce, I think, minus, I have to put minus here, minus, that will 2 in the numerator, right? And I need 1 here, so I will be balancing it by 1 by 2, right? So you can use partial fractions here at this step, or you should write it directly, right, to save time. And that is just a hit and trial. Write the first factor plus or minus, two possibilities. If you take plus, then that will produce 2z in the numerator, but I don't need 2z, I need 1. So I put minus sign, but on taking LCM, I was getting 2 in the numerator, so I balanced it by the factor 1 by 2 here, right? Okay. So this is partial fraction technique, okay? And now, therefore, I equal to integral C, and this is my dz over z square minus 1 is equal to c dz over z minus 1 by 2 minus 1 by 2 dz over z plus 1, right? Okay. Now, if you see this integral, right, you see this function is 1 over z plus 1, and this function is analytic inside this c, right? You just compare this function with this letter c. Function is 1 over z plus 1 is analytic inside c. You can check it from here, right? Actually, the singularity point is z equal to minus 1, and that is lying outside the curve c, right? Means that this function is analytic inside this curve c, so we'll be using Cauchy's theorem, and due to that the answer will be 0. This will give you 0. This integral will go to 0, right? And you should know the reason why. Cauchy's theorem, right? Okay, this theorem. Cauchy's theorem integral fz dz 0 whenever fz is analytic. This is analytic inside this c. Okay, fine. But what about this? Equal to 1 by 2 integral dz over z minus 1 c, right? Can we use that formula? Formula number A, result number A? Yes or no? Yes, obviously. See this. The singularity is z equal to 1, or you can say that the function is 1 upon z minus 1, right? Inside the contour c, you can see it from here. And you again see that the c is enclosing one and only one singularity, that is z equal to 1. So we can apply that result number A here, and since its power is 1, right? So the answer will be 2 pi eta using that result number A. 1 by 2, 2 pi eta using result number A. Ultimately the answer will be pi eta, right? Okay, example number 3. And for that I will rub this first. Example number 3. Evaluate integral c dz over z square plus 1, where c is mod z equal to 3. That's fine. Okay. Solution. First I will draw the curve, and the circle is centered at origin and radius equal to 3, right? Y-axis, x-axis. So this is a circle of radius equal to 3 and centered at origin, right? C. Fine. And now you check your function fz, whether it is analytic inside it or not. See the singularities of this function. If you put this denominator equal to 0, you will get z equal to plus minus eta, right? And you have to plot eta and minus eta here. This will be z equal to eta, obviously. This is z equal to 3. This is 3, so eta will be something here. Z equal to eta, and z equal to minus eta will be here. And this time, if you compare these two questions, both of these singularities are lying within C, while in that question the one of the singularity was lying outside, so the case was simpler than this one, right? Okay, now I have to draw circles, new circles, right? Because if you want to treat it this C as C1 or C2, that is not possible in this case as it was possible in that case, right? Because that was enclosing only one singularity. This time a circle is the original contour is enclosing two singularities, right? So we have to draw two separate circles, C1 and C2, right? And let those circles be this one, C1 and C2, C1, and this is the C1, and this is C2, right? And you just take care of one thing, that these two circles should not intersect, right? Okay. This is C2. And what is the radius of this circle? That is arbitrary, means it should be less than 1 or equal to 1, right? Less than 1, fine. And this is less than 2. I will take the radius R1 and R2, right? And obviously R1 should be less than 1, R2 should be less than 1 in order to avoid overlapping, right? Okay. So first I will write this fz. Fz equal to 1 over z square plus 1, and since it is 1 over z plus eta into z minus eta, and then applying partial fractions, I will write it as 1 over z minus eta, and here I should have minus 1 over z plus iota, and on taking LCM I am getting 2 iota in the numerator, so 1 upon 2 iota should be the balancing factor, right? So this is by partial fraction. Okay, now therefore I is equal to integral c dz over z square plus 1, fine, will be equal to integration c 1 over 2 iota dz over z minus iota and minus 1 over 2 iota dz over z plus iota, right? And this step is obviously for that, in order to use that relation number a or result number a, because we don't need anything in the numerator, and the denominator should be precisely of the form z minus a, right? Okay, and at this point, right, I will draw two new contours C1 and C2. However, I have already drawn them, so I will write it here, making circles C1 and C2 around z equal to iota and z equal to minus iota, as you can see from figure, such that the first circle is mod z minus iota, the center is iota, first circle, and radius is, suppose it is small r1, right? And second circle is mod z plus iota, it will become plus iota, and this radius is less than r2, right? Should I write it equal to, sorry, these are circles, not discs, where r1 is less than 1 and r2 is also less than 1, in order to avoid overlapping, right? So the problem will be converted. Again, you remember that Cauchy's theorem for multiply connected domain. The problem of integrating the function around the outer contour is actually equal to the problem of evaluating the function fz over these small contours C1 and C2, and then we add them to get the final result, right? So now I am going to apply the theorem on this I. Therefore, I equal to integral 1 over 2i, and this integral can be written as C1 dz over z minus iota plus C2 dz over z minus iota, means these two integrals for this integral, minus 1 over 2 iota. This integral can be written as C1 dz over z plus iota plus dz z plus iota C2, right? Okay, equal to 1 over 2 iota, right? And you just see this point is z equal to iota. Whether this z equal to iota is enclosed inside C1 or not, you see this figure. Yes, z equal to iota is enclosed inside C1, right? And now we can use that result number a, right? And according to that result, since this power is 1, the answer will be 2 pi iota, right? And plus, if you see this point z equal to iota, and see the curve C2, z equal to iota lies within C2 or not, you check it from figure. Z equal to iota does not lie within C2, so you can say that this function is analytic within C2, right? And now you can use the Cauchy's theorem, and the answer will be 0. I will write here why. 0 is due to the Cauchy's theorem, right? The function is analytic over this C2. You just check this function over the contour written here, right? Okay, minus 1 over 2 iota, and now you check the function 1 over z plus iota, and this is not analytic at z equal to minus iota, but fortunately z equal to minus iota is not lying within C1. You can check it from here, right? So we can say that 1 over z plus iota is analytic within C1, right? So the answer will be 0, and this is due to the Cauchy's theorem, right? And now the point is z equal to minus iota, right? Similar to this one, z equal to minus iota, whether it lies within C2 or not. Check it. Yes, it lies within C2, right? So C2 is enclosing the singularity z equal to minus iota, right? And this is the only singularity that C2 is enclosing. So we can again use the theorem number, useful result A, and the answer will be 2 pi iota, since the power is 1 here. In place of n we have 1. Okay, so ultimately the answer will be 0, right? So you used the Cauchy's theorem for multi-connected domains also, right? But to use that Cauchy's theorem for multi-connected domain, you need a result number A. That is very important result, right? We use that result directly, and the important part of the theorem is that for both simply connected as well as multiply connected region is that you can always replace an arbitrary contour, or you can say a complex contour, right, or a contour of any shape can be replaced by simple circles. Means whether it is the outer C is a square or is a triangle, hexagon, pentagon, any figure, it can always be replaced by simple circles, right? And those circles must enclose one singularity. Means the C1 circle must include first singularity, C2 only one singularity, and that is the necessary condition to use this result number A, right? This is it for this video. In the next video, we'll be doing something more on complex integration, right? Thanks.